The universe is a fascinating and intriguing realm, full of secrets and extraordinary happenings. This is most likely why certain individuals are always afraid while discussing space and astronauts. And what could be more terrifying and appealing than a black hole? Hundreds of studies have been published on these unique objects, which are the most intriguing subject to examine in astronomy. Last year, when the Event Horizon Telescope captured the first photograph of a black hole revealing the magnificent hole located in the center of the M87 galaxy, the whole scientific community and even the global population was completely enthralled. Imagine them as massive amounts of mass gathered in small volumes with such a strong gravitational force that nothing, not even light, can escape from the object. In reality, their name provides a fair symbolic explanation. Like holes, everything continues to sink in with no way out. Abandon all hope. Ye who enter here, reads the inscription that Dante placed at the gates of hell in his Inferno. This would be an accurate description of the phenomena, but don't be alarmed. You won't be eaten by a black hole. Instead, have you ever considered the genesis of these objects? How do they form? Are they formed in a single way, or are there various forms of formation? How long does the birth of a black hole last? How can we trace the beginnings of this phenomenon? These and other questions will be addressed in this video, so if you're interested, please stick with me and I will tell you everything in a moment. We'll be looking at one of the most essential items in modern physics. Therefore, we'll go over it step by step to get a better understanding. Who initially proposed the existence of black holes? The concept of a planet so huge that even light could not escape was briefly mentioned by astronomy pioneer and English clergyman John Michell in a letter published in November 1784. However, when physicists discovered the wavy character of light in the 19th century, Michell's theory was abandoned because it was unclear how and if gravity could interact with electromagnetic radiation. To summarize, let us jump right to 1915, when maybe the most exciting idea in physics was published by a Swiss man. Do you know what its name is? Albert Einstein. He originally established special relativity in 1904, its renowned Annus Mirabilis, and later wrote another essay describing the photoelectric effect, which earned him a Nobel Prize in 1921. Around 10 years later, in 1915, he published general relativity, which is considered one of the most fundamental theories in physics. But what does general relativity state? How can we intuitively understand such a complex model? Shortly thereafter, Einstein attempted to apply his special relativity to gravitational events such as planets orbiting a star or stars colliding at high speeds. He discovered an important result: an object's mass causes space and time to be deformed. What does this mean? Imagine the space-time continuum as a large cloth sheet. When a sphere with mass, the Sun, is placed in the center, the sheet curls. If another lighter object, the Earth, attempts to travel in a straight path through the sheet, it begins to move in a circular pattern around the first one due to the sheet's curvature. What effects does a star's mass have on time? When it comes close to an item, time dilates and slows down. Furthermore, as the body becomes heavier, the flow of time slows. What is a significant implication of this model? Light is affected by gravity because it must follow the curve of space-time. For example, if a large black hole is positioned between us and a bright star, light will deviate due to the deformation caused by the hole's mass. However, not only Einstein made significant contributions to discovering the theoretical existence of these particles. Indeed, within a few months after its publication in 1915, scientist Carl Schwarzschild discovered the solution to the general relativity equations for a spherical mass and a point mass. Just a few years after Schwarzschild, Johannes Droste, a student of Hendrik Lorentz, independently proposed the identical solution for the point mass and wrote extensively about its features. This solution exhibited unusual behavior at what is now known as the Schwarzschild radius, where it became singular, implying that some of the components in the Einstein equations were infinite. What were the two most unusual qualities of these singularities? First, the gravitational force would be so strong that light would be unable to escape, with rays falling back to the star like a stone to the ground. Second, the mass would cause so tremendous curvature in the space-time metric that space would close in around the star, leaving us out. As a result, the most significant discoveries were made during the so-called Golden Age, which began in the 1960s when black holes became the most prevalent and mainstream area of inquiry. In 1958, David Finkelstein used the term event horizon to describe the surface defined by the Schwarzschild radius. What exactly does this definition mean? The event horizon is roughly defined as the border where the black hole's escape velocity exceeds the speed of light. To be more specific, it is the point at which all conceivable light paths begin to collapse into the black hole, leaving no route out. Does it appear difficult? Don't worry. Here's a simple analogy. Within the event horizon, all light is guided into the hole in the same way that we go in the positive direction of time. This is an unchangeable order of the phenomenon that cannot be changed. Do you wish to know something alarming about these weird objects? When an object falls into a black hole, any information about its shape or charge distribution is evenly spread throughout the black hole's horizon and lost to outside observers. What does this mean? Practically, we can think of the item as a dissipative system, akin to a membrane with friction or electrical resistance. Whatever disappears into the hole is completely unavailable to outside observers. This behavior is so unique that it is dubbed the black hole information loss paradox. But let's get to the primary point of this video. What is the genesis of black holes? To answer this question, we need to discuss stars. But why stars? Because in astronomy, practically everything is linked to the breathtakingly bright celestial bodies that illuminate our black night sky. Scientists have discovered that stars evolve in different ways depending on their masses. They are primarily distinguished by the nuclear reactions that occur in their course. Nuclear fusion is critical for life formation because the reactions produce enough radiation to warm the planets orbiting them and even balance the gravitational attraction that would cause the celestial body to collapse on itself. How is this possible? Nuclear reactions dissipate a relatively small fraction of the mass involved in the process, resulting in enormous energy according to Einstein's famous equation E=mc². These tremendous amounts of energy are subsequently radiated as electromagnetic radiation on various scales: visible light, UV rays, gamma rays, or microwaves. These emissions have the ability to not only heat matter, but also put tenuous pressure on particles. In fact, the radiation released by stars functions as a breeze, counteracting gravitational contraction. Although radiation pressure is insignificant on Earth, it may be measured quite well in space. As a result, in 2010, Japanese researchers were the first to launch ICARO, a probe that uses stellar wind to traverse through space. Returning to the evolution of stars, heavier ones often have shorter lifetimes because they use hydrogen and other key elements, such as helium, for nuclear processes at a higher pace. Throughout its existence, the star spends varying amounts of time in different stages, depending on the major element burning in the core. In the case of enormous objects that are 8 or more times heavier than our Sun, the process of nuclear reactions in the core ends with the formation of iron. But why? Because fusing of its nucleus would require too much energy to occur. What is the outcome of this? The star's internal pressure, which was initially provided by radiation pressure, plummets drastically and fails to oppose gravitational contraction, resulting in a gravitational collapse. Practically speaking, the star collapses under its own weight since there is no longer enough pressure to balance the natural contraction. Now we must raise one question. Is there an inferior limit for the collapse of the star? Well, yes. It is also tied to quantum mechanics, an astonishing theory. The most essential aspect of this model is the Heisenberg uncertainty principle, which asserts that we cannot know a particle's position and momentum at the same time. Specifically, it stipulates that the product of an object's uncertainty in location and angular momentum must be greater than a constant amount. So if we know a particle's coordinates well, we will have a large inaccuracy in calculating its momentum and vice versa. In addition, it is vital to explain the Pauli exclusion principle. Simply put, two separate fermions, a type of particle that includes the electron, cannot be in the same quantum state. What does this mean? It indicates that two particles with the same position must have different momentum. How do these ideas apply to a collapsing star? In rare situations, the contraction is halted by the so-called degeneration pressure. The more densely particles are packed together and forced to share the same space, the more they must differ in terms of momentum. As a result, the greater the range in momentum, the greater the fraction of particles with high momentum, which exerts pressure on their surroundings. As a result, This mechanism permits matter to condense into an unusual denser state. The result is one of several forms of compact stars. Which type forms is determined by the mass of the remnant of the parent star that remains after the outer layers have been blasted away. The mass of the remnant or collapsed item that survives the explosion may be far smaller than that of the original star. Stars with more than 20 solar masses before the collapse produce remnants larger than 5 solar masses. For smaller remains, the collapse results in the production of a neutron star, which is a very small object made up of ultra-dense degenerated neutrons exerting a strong pressure that balances its gravitational contraction. If the remnant's mass reaches roughly 3 to 4 solar masses, either because the original star was very heavy or because the remnant gained more mass through matter accretion, even neutron degeneracy pressure is insufficient to prevent collapse. No known mechanism is powerful enough to stop the implosion, and the object will eventually collapse under its own weight. This is the formation of a black hole. Do you wish to learn something unique about this event? Because of time dilation, which is particularly significant in these vast expanses of space, an external observer will never see the end of this process. What does this mean? A spectator watching the collapse would witness the infalling material slow and stop just above the event horizon. Light from the falling material takes longer and longer to reach the viewer because time is warped by the large amount of mass. Thus, the external spectator never observes the development of the event horizon. Instead, the collapsing material appears to become dimmer and more redshifted, eventually fading away. In conclusion, black holes are typically produced by the leftovers of a collapsing giant star that is more than 8 times heavier than our Sun. As a result, several issues remain to be resolved, the most of which concern the possible death of a black body. Many aspects will be investigated to provide us with a better understanding of these extraordinary objects that constantly swallow everything within the event horizon. This video ends here. Thanks for watching, everyone. Did you find this topic exciting? Are you fascinated by the development of a black hole? Do you think it is conceivable for humans to get closer to one of these objects? Let us know what you think in the comments below, and remember to like, share, and subscribe.